This project is on neuron-controlled prosthetics by Graef,
Chase Henry,
Quinn, Tirpak.
The idea of neuron-controlled prosthetics is simple. The mind controls the artificial limbs. This is done by measuring the firing of neurons in the brain and converting these measurements to signals that can be interpreted by a control system. The idea is that amputees would be able to think about moving their missing limb or limbs, and the prosthetics would respond in the same way and at the same rate as the actual limb.
DARPA started a project on neurally operated prosthetics back in 2006 with $120 million in funding in order to create better prosthetics for wounded veterans. In early 2015, Johns Hopkins University completed initial testing and have sent the project in for approval by the FDA.
These neurally powered prosthetics act as a discrete system modeling a continuous system. The interaction between the brain and limbs is instantaneous and considered continuous, whereas there are slight delays and errors in the neuron modeling, making the neurally powered prosthetics a discrete system.
In this system, the inputs are the neuron impulses sent from the brain to where the limb would normally be. The number of impulses in a 100 millisecond time span is recorded and called the spike count. The spike count for each neuron is then passed through a mathematical model that converts the spike count into the desired state of the limb. This system uses the angular equations of motion. The equations seen here are the quaternion rate equations. These would be similar to the equations used in the prosthetic modeling. Once the neuron signals are mapped correctly, the prosthetic moves in the desired way to the desired orientation. The measurements of this orientation are taken and fed back into the feedback control law.
In order to function similarly to a real limb, feedback control laws are utilized. In the example of a prosthetic arm, the hand should mimic a human hand. The fingers should not need a long settling time to reach the desired outputs, as well as having a very small magnitude of the peak overshoot. In order to simulate the continuous feedback control laws used by a human, the prosthetic human system uses a PID-style controller. The neurons send an initial input to the system, which maps to an electrical impulse that is used as the input to the actual control system. The servo motions are measured and relayed back to the nerves as feedback. The body senses these and converts them to rates, which it uses to send new input back down to the prosthetic. This is similar to the way a person eases off the gas as they come up to speed in a car.